Hello friends, welcome to this session. In this session, we are going to study various turn-on methods of SCR. Switching SCR on or turning on SCR is called as a triggering. Switching on of SCR is called triggering. And there are different techniques. In last session we have seen that how gate current plays important role in turning on of SCR, but these are the different techniques and each technique has some advantages and disadvantages and some applications also. So let us consider we have five basic triggering methods. The first one is the voltage triggering, then we have radiation triggering, thermal triggering, dv by dt triggering, and the last one that is a gate triggering. So let us study one by one. In case of voltage triggering, as the name indicates here, we are going to apply that is a voltage between anode and cathode. We have seen in the characteristic of SCR when the SCR is forward biased and when its anode voltage reaches to a specific value, we call it as a breakover voltage. Then because of that alpha 1 plus alpha 2 condition, suddenly SCR turns on. So this is the simple technique, but not convenient one, because you have to increase the voltage to a very high level. This technique is called as voltage triggering method. Then we have radiation triggering. This one, that is the radiations. In this case, this SCR, we have seen that it has three junctions and four layer PN junction J1, J2, J3, and this is the gate, right? And this is the anode and cathode. See here we apply VAK. Now suppose that this SCR is forward bias, and because of that this junction J2 gets reverse bias. This particular junction gets reverse biased, right? And if there is some window, glass window, if we keep glass window here, and if we incident on some light, photons, or some high energy neutrons, so these photons or neutrons are source of energy and they will create here current carriers, electrons and holes. These electron holes can flow under the influence of this anode and cathode voltage, and that may trigger this SCR. That's why it is called as a radiation triggering. In this case, gate may not be connected anywhere, so just having some voltage forward bias, and if there is a flush of some light or neutrons, that can turn on the SCR. So it has application, and we have the special device for this light activated silicon controlled rectifier. We shall see this later. Then we have the third type, that is a thermal triggering. As the name suggests, the SCR is forward bias. Some positive voltage is given here between anode and cathode. You may have get connected somewhere, and some VAK is applied, right? That means SCR is forward bias, and with forward SCR we have always junction J2 as reverse bias, and if due to any reason the temperature of this SCR increases, so as the temperature of this reverse bias junction increases, this thermal energy, heat energy, creates current carriers, holes and electrons, and they flow under the influence of anode to cathode voltage, and at a particular heat, at particular temperature, this SCR fires. So that's why this technique is called as a thermal triggering. Then the next is a dV by dt triggering. So dV by dt means this is a SCR, this is anode, this is a cathode, and this is a gate. And suppose that this is junction J1, junction J2, junction J3, right? So here idea is that we are going to apply voltage between anode and cathode at fast rate. So this dV by dt, that means rate of change of voltage with respect to time. So voltage may not be large, but if time interval, time taken to rise that voltage is small, in that case this value will be higher rate of rise of voltage. And here there is one interesting thing. When this SR is forward bias, this particular junction is reverse bias, and for every reverse bias junction there is a critical rise of this voltage reverse bias at which it begins to conduct. For every diode, for every junction, reverse bias junction, there is a critical, a fixed value of dV dt beyond which that junction will break down. Though it is a reverse bias, it will start its conduction, right? And the same idea is used in triggering the SCR. If we apply here anode to cathode voltage at the rate greater than that critical rate of rise at junction J2, in that case then SCR will turn on, and that's why this technique is called as dV by dt triggering. And the last and very important one and mostly used in industry is gate triggering circuit, right, or gate triggering. In this case we have seen actually this by injecting small gate current, this gate current triggers the SCR. We have also studied the expression for anode current as alpha 2 Ig upon 1 minus alpha 1 plus alpha 2, right? So this expression states that how anode current depends upon the gate current. So this technique is very convenient. So you can apply or inject the gate current in different ways. So what are the different ways? By just using the DC gate voltage, and that is called as DC gate triggering. The name itself indicates that by applying DC voltage to the gate like this. So this is just a sample circuit where this is the SCR, there is a load and the power circuit is there where power is to be controlled. Look at this gate. This gate is connected to some source, and we call this as, this circuit is called as a control section, and this is the main power circuit, right? So here Ig is injected, and it depends upon the voltage here, and this voltage depends upon the how much current you want, and that also depends upon the this series resistance. So in DC gate triggering, we apply DC voltage of a proper magnitude and polarity so that it gets triggered. So there are two drawbacks of using the DC voltage. With DC voltage, isolation is not possible because a gate control circuit is directly connected to the gate, and this SCR is directly connected to high voltage. So there can be a sort of feedback from high voltage power control circuits to low you can say the control circuit. So isolation is not possible, and as DC source is continuous source, even when the SCR is turned on and turned off, always gate current will flow, and because of that gate current, gate losses increases. So these two are the main disadvantages with the DC gate triggering. Then what is solution to this? you can have that is a AC gate triggering. So if there is a AC voltage source and you are operating some SCR in AC circuit, in that case it is possible to use AC voltage like this, which are occurring periodically, and you can change the phase of this gate pulses or gate input, so that you can trigger the SCRs. So as you are using the AC, it is possible to have isolation just by using transformer, pulse transformer, or transformer. You can use in transformer, you know that primary and secondary circuits are not physically connected. So gate current will flow in this primary, and this induced voltage that will induce current here in SCR, and SCR can be triggers. So this is a more convenient than the DC gate triggering. Here also again you can improve this in the last one, that is pulse gate triggering. In this case some power loss occurs, but in case of pulse gate triggering we use pulse generator like a UJT sawtooth generator, where we get pulses like this. If this is the time axis, then voltage increase sharply like this. These are called triggering pulses, or you can say these are just a voltage pulse of very narrow lifetime, narrow pulse width, you can say, right? So such a train of pulses can be applied to a gate of the SCR, and the very first, if it meets the requirement of that SCR, the very first pulse will trigger the SCR, and after triggering, you know that gate loses its control on the SCR. गेट अपना कंट्रोल खो देता है. Gate has control on SCR only when it is off, and after firing gate loses its control, right? So by applying such a train of narrow pulses, it can trigger the SCRs, and here we have both advantages, that these pulses can be applied using the pulse transformer, so isolation is possible, and these are the short duration pulses. There is a no power loss, gate power loss. So these are the advantages. So these are the different techniques of triggering SCR, and the last one is the most convenient and mostly used. Then we want to discuss some important parameters, or let us consider some definitions like this. For example, we have this, say, maximum on state voltage. This is a parameter of SCR, characteristic of SCR. What it says, maximum on state voltage. We have seen that in the characteristics, as SCR turns on after firing, the anode to cathode voltage drops to very low level and conduction begins. So what is the voltage when there is a conduction? That is on state and maximum value. So that is called as a maximum on state voltage. Normally it ranges from 1 volt to 5 volt. It depends upon the structure and the rating of a given SCR. Then we have peak inverse voltage. Peak means maximum, inverse means reverse, ulta voltage. That means when SCR is reverse bias, negative positive like this, so how much maximum voltage it can withstand without breakdown? How much maximum voltage, reverse voltage, it can withstand without breakdown is called as the peak inverse voltage. Of course, it is in kilovolts. It is very large. Then other parameter that is used to characterize the SCR, that is T on time, that is the turn on time, and it is expressed, the symbol is like this, T suffix on. Turn on time, you can this name itself indicates that it is the time taken by SCR to turn on. To turn on means to go from blocking state to conducting state, off state to on state after triggering. So after applying triggering pulse to the gate, how much time that SCR takes to turn on, that is called turn on time. And you know that the condition for turn on, that anode current should cross, or the anode current should increase above latching current. This is the required condition. Then we have turn off time, and is written like this, TOFF, right? Turn off time. Now you can say that how to turn off the SCR, by reducing the anode to gate voltage. Once SCR is fired, once SCR is conducting, you know that anode to cathode voltage is just 1 to 5 volt. So if you reduce this voltage or reduce this anode current, when this anode current drops below the holding current, you know that holding current is the minimum anode current required to hold this SCR in on state, and when this anode current drops below the holding current, SCR turns off. So turn off time is actually time taken by the SCR after that current has dropped below the holding current. So just time taken to turn off the SCR after removing the, you can say, the triggering reduction in the anode current, that is called the turn off time. So these parameters are required while designing the control circuits. Then we have some parameters like this, IG minimum and VG minimum. IG means gate current and the required gate voltage for that current, right? So the name itself indicates it is the minimum gate current required to turn on SCR, or minimum gate voltage required to turn on SCR. This gate voltage depends upon, to get a IG minimum, what should be the VG minimum, that is decided by this biasing resistor, right? The gate resistor. So they are interrelated. These two things are related to the value of that resistance. So minimum values mean minimum values of VG IG required to turn on the SCR. And there is a one more parameter, that is a IG max and VG max. As the name indicates, these are the maximum values of the gate current and gate voltages that SCR can tolerate. It means that if you trigger the SCR with the more current than this or more voltage than this VG max, that gate junction of the SCR may get damaged. That will destroy the SCR junction, and therefore in no case the gate voltage and gate current should cross this level. So this is the IG max and VG max, maximum value of the gate current and gate voltage, that should not be crossed. So these are various important parameters associated with SCRs. So let us stop here. If you have any problem, difficulty, any suggestion, please put them in a suggestion box. Thank you so much for viewing this video. Bye.